Hey everybody, happy Thursday. How you folks doing? Sorry I'm missing you in person again. My daughter's still not doing great, but on the mend. Been it's been quite the week. So sorry I missed you on Tuesday. So we are a little bit behind. There's a third project and the final project, and I think at this point we might just want to skip that third project because we're, trying to get everything else in because we got to get started on the final project soon. So I think we might just end with just the three. I don't know, because to take 2 weeks to do it will put us out to mid-April, and then we only have like 2 weeks left to get the final project done, and that's not great. So I think we might just miss that other project. Let's take a look and see. Because we can talk about hash maps today, and then we can get into search trees on April 5th and sorting and selection on the 7th. Yeah, I think that's probably what we'll need to do. So we'll finish up hash maps today. We got started on, we didn't actually write any code for them, so we'll write the code for it today. And then next week we'll pick up search trees. The sorting and selection is real quick. There's not too much to it, so we shouldn't take the whole time. And then anything we need to bump into this week, we'll have a little bit of time there as well. And then we are the last final day, or almost the end of the final day. So I think will give us all of April then if we start the final project coming up next week. That sound like a good plan? I think we can do it that way. All right, so let me pull up. Oh my goodness. Wow, PyCharm. I got nothing. Nothing's in the brain today, folks. All right, so we'll take a look and see if we can't build out our own hash map. Again, there's good things we can do. Again, we're not going to go for the super crazy advanced stuff because it's already been written. We just want to go for a basic level of understanding to see if we can figure out how to implement it. We don't need to do the prime numbers and the next, double the size plus the next prime number and all sorts of that fun stuff for indexes to get that better distribution. Because a lot of what this relies on is assuming we can get a uniform distribution or close to a uniform distribution across all of our entries. Right? So as we take the data and we hash it, we want them not all to end up in the same bucket, because then we end up with the thing. But overall, it should be pretty close. So let's take a look. Let's see if we can start up a new project. As soon as this loads, give it a second. Still working on it. Come on. It's been a week. Friends. All right, here we go. New project. Call this one hash maps. Okay, so we're going to write our class for the hash map. Here, let's see, that's a little small. Let me zoom that in for you. There we go. So when we create one of these hash maps here, Hector, my friend, thank you so much for coming by and donating those bits to the Student Scholarship Fund over at the University of Michigan Dearborn College of Engineering and Computer Science. We are funding that scholarship. We're working on it. So we had the Giving Blue Day was that last week, 2 weeks ago, where we actually crashed the website because so many people wanted to give, which was pretty cool. So awesome to see that support. Thank you, my friend. All right, so the init method here. So the hash map, what it's doing behind the scenes is we're going to have a self.storage, or maybe we'll call it storage here, is just going to be a list. Right, and we really want this none. We want it to be size 10 or so to start. Again, 10's not great. I know it's not great, but that's okay. We'll figure it out after the fact, and see what we can do with this, managing, getting these items in and out here. Okay. Then we're just blank, and then we need the self.number of items. Number of items is 0, and then we can define is empty. Return self.number of items is 0. There it is. Wow, my friend. Thank you so much for donating those bits. Those are going to the Student Scholarship Fund over here at the University of Michigan Dearborn College of Engineering and Computer Science. First time chat as well. My friend, how did you find us? So glad to have you along here. Twitch has just been so generous, which is so cool. We've raised over $250 or $300, I think, now towards the scholarship fund, just because I think Zoom is awful. And I prefer doing stuff on Twitch because I'm a big nerd. So welcome on into class. Equals 0. There we go. So we're empty if we have nothing here, and we can define length as well as return self.number of items. Oh, great. Oh, thank you so much for coming along. Yeah, glad to see you here. Yeah. Okay. It's all coming together in my head here. I'm a little slow today, so thanks for dropping on by. We're doing some Python today. All right. So we can store items in our internal storage here. We can figure out if we're empty. We can figure out our length. Now we need to be able to actually add an item. So there's a couple of these extra get item and add item that we're going to start overriding here as we go. And I'm actually going to go and grab a copy of the book here. Thank you so much. Yep, take care. I appreciate you dropping by, my friend. We'll let me go grab the copy of the book here to make sure I'm not doing this wrong, because honestly, it's been one of those days. It's been one of those days. So we'll follow along here, mostly. We're gonna take a slightly easier route for it here. I don't think we need the full everything as we go. So we'll start off not as a map too. We'll be just a, maybe we'll start as a map. That might be easy enough. Where we can store a key and an associated value. Grab that chapter here. There we go. Yes, okay. Oh man, they got all sorts of this stuff here. Yeah, they go through and do all this ugly stuff. I forgot how much he uses inheritance here. Okay, we'll try some of these here. We'll try some of these. Yeah, we don't need the scale, we don't need the shift. Hash is fine. Okay, so we're going to have a this idea of a bucket, right? So we talked about when we draw stuff out with a bucket here. Let me see, is this, oh, I didn't do word, this is just a screen capture. Let's see how well this one works. We'll just draw right here. So we're going to make this list here, right? We have this storage data, and we're essentially going to get 10 slots in here. Each one of these is going to be a bucket that we're going to drop items in, right, at a given index. And the bucket then will point to, right, it's a single linked list for each item here. I think it'll work out really well. So we can start adding these buckets in here. So as we hash something, we say, oh, let's add in the number 27. We'll hash it. We'll figure out it probably goes to slot 7, 0, 1, 2, 3, 4, 5, 6. That's close enough, right? 7. So we'll drop it in here. There's nothing there. If we drop something on top, then we'll add the next item on top and point to what's currently in there. It gets a little bit crazy here, but we're going to make this work with our buckets. Okay. So to do this, now we need a item. So we use this inner class for item to store the key and value pair. We'll go grab and make sure we got item here. where'd it go? Here's our item class. So we're going to have an internal class for item. Init, and it needs the key and the value. We're going to use a key value pair. So we'll have self key is the key and self value is the value. This is the pair of items here then. We're going to find if they equal each other. If the self.key equals the other.key. Okay, define not equals other self and other as not self equal other. Right, we've already defined one, we don't need to define the other. And then we can define a less than if we want here. Less than self and other. We can say we're going to return self.key is less than other.key. Okay. So we got these ones here. So it says we're accessing the private values. That's okay. We're in here. It's not too bad here. So then we need our... That's it. That's the entire map base class. That's fun. That's awesome. Okay. So now we'll go through and start building this out here where we've got our data, our storage here. So we could be a little cleaner if we wanted and have this capacity be a number. We probably should do that. So we'll have a capacity, or starting capacity maybe. Starting capacity is 10. There. Just be a little cleaner here. Self.starting capacity. Oh my goodness. Not typing. Keyboard. Work with me here. Work with me. It's like all locked up here. That's awesome. Is it Friday yet? Starting capacity. Okay, there we go. So we have the starting capacity here. And then we're going to have a way to get the hash out. So we need a hash function here, which will generate the hash of a given key. So if you tell me the key, I'll give you the hash of it. So what we're going to do is we're going to get the hash. Now hash is a built-in function here. So hash is something you can do, right? This is a built-in function. That's why it shows up purple here, of the key. Right? So we need to figure out what the hash is, and then we need to modulus that by the length of self.storage. Again, this is not the best version here. Right? I guess we can get rid of those parentheses here. This is the easy way here. Easy method. Not ideal, right? Throwing in some prime numbers there, and doing this sort of thing here is great. We're not going to worry about that. We're just going to say, okay, let's just take the hash, modulus by the length, and assume we get the right thing here for our hash function. What is this even doing here? I have no idea. I think my computer is ghosts. Okay, so then to set an item. So setting an item, given a key and a value. That's where we say, dictionary key of this equals a value. So we need to find out what the hash is. So our hash is going to equal self.hash function of the key. Okay. Then we need to do this bucketing stuff here. So to do the bucketing stuff is a little bit funny here as we go. So we know what the hash is. Now we need to go see if there's a bucket there. So this they added in as a helper method here. So we're going to call self.bucket set item given the hash, the key, and the value. Okay, and then we're going to see, hey, if the so it's setting an item. Where's my number of items? That should be going up, right? Bucket set item. Okay, yep. So if my self.number of items is greater than, and here's where we're going to see there's some sort of load factor. So we're going to say a load factor, we'll say is 2. So We want to get to no more than 50% full with our hash map. Again, the idea, the larger we are, we're taking a little bit more memory, but we're going to have a better chance to have a better distribution. So this is all about getting that good uniform distribution across all of our buckets here. So we're going to go with the load factor. Or how about 0.75? We'll try that. We'll go up to like 75% here. So we'll say, hey, if the number of items is greater than the length of self.data, storage, right? Self-storage times the load factor. Self.load factor. So if 75% of the length of the storage here is less than the number of items, then we're going to need to resize. So we'll call self.resize. Resize. Okay. So we haven't done either of these bucket things or the resize yet here. We'll get to all those. Okay. I guess that's hash value is probably better here. We don't even need to do that. We're just going to call bucket set item. They were doing this more inheritance stuff here. We'll just deal with it this way. So to set bucket item, set bucket set item. Set item given a key and a value. We'll go figure out what that hash value is. Hash value is, well, actually this is, I'm sorry, this should be the target index. The index will be self.hash function of the key. So this is going to be what index does it belong in, right? Because we're hashing the key, modulus it by the length of our storage. Okay? So we're going to see where it should go. Then we want to see, hey, if our self.storage, sorry, let me set my phone on silent here. It keeps ringing. Okay. If the self.storage index of the index is none, that means there's no bucket here, right? There is no bucket. So if there is no bucket, we'll go and add a bucket. And really, we don't even need to do the single sorted, singly linked list. That's probably harder than we need to here. Buckets could just be Python lists. It's not going to be quite as efficient here. This is easy, say Python list, but not quite as efficient. But it's okay. We're not going to worry too much about it here. So we'll say self.storage at the index then is equal to a list. Okay, then we're going to append an item given the key and the value. So if there is no bucket, right, we'll make a new list here. The list is going to essentially be our bucket, and we'll just add that item in there. Okay. If there is one, however, though, this is where it gets tricky. So we've had to add it here. So our self.number of items goes up by 1. Right? So we've successfully added a brand new list here. Otherwise, what we're going to do then is we need to look and see, does it already exist inside of here then? Right? If it doesn't exist already, well, then we need to go and find it. Okay, so all right, this is, wow. Yes, we did. Okay, so if we can cheat a little more too, and we don't want to use a built-in dictionary though, because we're trying to build our own dictionary. You could do another dictionary here, but we don't need to. It's okay. So if there is a list, we're going to say for item in self.storage, index of index, right? See if those items, right? See what items are in there. If the item, so actually we need to make a new item here then. We'll say a new item equals self item. I guess we don't even need to do that either. We can just say, we'll say if the item dot key is equal to the key, then we'll take item.value, assign it to the new value. So if we find one that matches, right? Items have keys here. If we find one that has a matching key, we could make another item and then have this equals thing. That might work. It might be more trouble than it's worth here. It's probably okay, one way or the other. So if we find a matching key, update the value. So this is if it was already, or if that key went, right? If the key already was in there, update the value. Right, and at this point, we'd actually want the old value as well. So the old value is my item.value, set it here, and then we'll return the old value. Right, if we've looped through all of those and we haven't gotten there yet, we're going to go and append it. Right, so if we don't find a matching key, we'll go and append it in. New key, add the item. Right, so if we do find it, go and update it, return the value. Otherwise, it's gone. Right, so this is the set or update here, essentially. Okay, so to set an item, call bucket set item, and then see if we need to resize. So bucket set item, if it's empty, add it in. If it's not empty, look to see if there's a match. If not, add it in. Okay, and then there's a define a get item. Given the, and this is really the key, essentially, here. We're going to call it key. So we need to find the hash of it and go get the value back out. So the get item here, we could have a separate function for it, like this one had. I don't know if that's really necessary. You know, let's just cut that one out. I'll just do all this here. We don't need that separate function for it. We'll just do it right in here. It's not too bad. It's not too long here. So if we're getting an item, we'll get the index then. Again, is going to be the hash of the key. Right? And we need to see, hey, can we go get the item back out now? Right? So to go get our item then, if we're going to see if we don't find it, right? So then our, if self.storage at the index is none, we're going to raise a key error, right? Not found, right? We don't have that key. Otherwise, then we're going to say for item in self.storage, storage at the index, if the key equals the item.key, return the item.value. If we haven't done that, right? After we loop through all of them, we'll raise a key error again. Not there, right? Doesn't exist. So it's either empty, or we can loop through it and find it, great. Or if we've looped through, we didn't find it, raise another key error. So we can get an item, we can set an item, we can add delete item as well, delete item. So define delete item, given a key here. We're going to get the index again. So getting this index we do every time. We need to go find where these things go, right? And then if we are bucket's empty, right, raise a key error. Otherwise, we're going to go try and find this thing here. If it's not, so now this one, if it matches, right, we need to get the value. So value then is equal to my item value. Right, and then we need to delete the item out of the storage. So to do that, we probably actually want, let's loop through this by index. This might make this easier because when we loop through by index, we'll say for index in range length of self.storage at the index, right? How long is this internal bucket essentially here? Or say if the self.storage at the index here, oops, we shouldn't have index twice here. So this is hash index at the hash index. So for index here, if the self storage at the hash index at the index is equal to the key. Oh, that's the item there, so that's dot key equals the key. Right, so self-storage at the hash index is what bucket it's in, and then inside that bucket, what index is that one in? There, for each item in that bucket, if the keys match, great, we'll have the old value, or I guess the value, equals the value. Then I can take my self-storage here, and I'm going to call pop the index. So I'll remove that index, and I'm going to break my loop. We'll just return the value. We don't need to break. We'll return the value. So this will stop the loop from running. Remember, this is cleaner. You don't, I mean, I guess we technically could loop through and do it this way. You usually don't want to modify the loop we're iterating over. It'll be fine. Okay, I'm feeling bad here. So let's go back and change this here then. So let's undo a bunch of this. Sorry. This is too ugly. We'll go back. We don't need to do it because we're stopping right away. Okay, for item in self-storage of the index, if we match the key, we have the value. And then we're going to take self.storage. That's why, and we're going to... But we can't pop because we don't know what index we're at. That's why we were doing that. Oh, goodness. No, we can remove. Yeah, we can call remove the item. Because this is an item class, and item class has an equals method. So it'll go through and do this here, removing it. And then we'll return the value. So this should work. We'll try it. We'll test it out and see. We should be able to remove an item from our bucket here. Okay, so we can set an item, or we can get an item, right? Set item, get item, delete item. So we can do all of those ones. Now we need to figure out, well, how do we resize? Right? So the resizing is the tricky part. Resize. So to resize, we need to get all of our old values and all the new values and rehash them. Right? So to do that, what we want to do, we want to get all of the items back out of the old one. So we're going to take our old storage is equal to self.storage here. Now remember, this just makes a link to it. Right? So the old storage links to the new storage. So we have two things pointed to the same list in memory. This is just a Python list. Okay. Then I can say self.storage equals a new list here, none times, and we're going to take the length of self.storage, and we're just going to double it here. Again, this is not ideal, but easy. Right? And you want to have some factor and do a little bit easier, better than doubling here, but doubling will get the job done here. Okay. So now we have empty storage of twice the size here. Then we're going to say for this is essentially a bucket in old storage. Right? For each item here, right? If bucket is not none, for item in bucket, let's take self dot. We want to add, what is it? Set item. I think we can just say self dot item dot key equals item dot value. Right? I think this will call the set item. Right? When we call set item, if we have a larger storage here, the index hash that we get out, the hash function to get the index, is going to be a different value. Possibly a different value. Again, it depends on how we're doing our doubling here and whatnot. So it might get a little bit funny here. But we'll go through and take every item then. So if the bucket's not none, for every item in the bucket, go and re-add it to the new self storage here. We just go add them all, and that's it. So should we see if it works? Oh, and then we can add in an iterator as well. So we want to define an iterator of self. We're going to say for bucket, again, the same idea here. For bucket in self.storage, if the bucket is not none for item in the bucket, we're going to yield the item.key. Remember, when you iterate over a dictionary, a Python dictionary, you just get keys out. Okay, so we should be able to use this just like a Python dictionary. Now, again, this is not as efficient as a Python dictionary, but this is, essentially what's happening behind the scenes, right? We want a large storage capacity, oversized, and we're going to hash the items and throw them in. Again, hoping for uniform distribution, that sort of thing here. It ought to work relatively well. We'll see here how it goes. So we'll make a, my crappy dictionary equals a hash map. And then, I don't know, how about for value in range, let's do 10. Let's do 20, make sure that, the bucketing stuff works. How about 25? We'll take our crappy dictionary, we'll say key of the value equals, we'll just map it to itself, right? The key and the associated value. So if it starts at 10, we should get the first couple in before it has to resize, and then it'll double to 20. We'll get another bunch in before it has to redouble. It'll get up to 40. Again, hashing numbers here should be super easy. Shouldn't be super interesting. But let's give it a look. Let's see if we can run this in debug mode. Oh, let's do it before we go in debug mode. Let's see if we can just get the values out. And then for key in the crappy dictionary, let's print key colon crappy dictionary key of key, right? Get the item associated with it back out. So it should just be 00, 11, 22, 33, 44, on and on and on. We should be able to get all the items out. So we are able to get the items out. Worked okay so far. Not too shabby. So let's run it in debug mode here and see if we can see what's happening. Again, we're taking the easy route. We don't need to get super deep into a lot of the theory on this. We just want to understand how they work kind of behind the scenes. So our crappy dictionary then has storage here of a bunch of nuns. Right, that's what we'd expect. So let's run it a couple times. We'll step out a couple times, get a couple of values in here. So now we have a bunch of items inside of our storage, right? They're the item maps here. We have key and value. Right? We haven't had to double up any of these yet. Right? No big deal. So let's keep on going. So we haven't resized yet. So this next one we'll probably want to resize. So let's step into our code here. We'll hash it. We'll figure it out if it's there, append it, number of items, and check on resizing. So we should need to resize here. So we're going to resize our storage here. And we'll just step out. And now our storage, right, should be size 20. We should have doubled here. Again, our hashing here is really easy, right? Hashing the numbers hash really nicely. So we haven't seen any doubling up yet. So what we can do here, if we want to force some of that to happen, we can either do random values, or we can change our load factor to say like 1.5. So I can store 150% of 10 items in a single storage. So this will force us to have some of that doubling happening here. Right, so I can store 15 values in size 10 because I'm going to make them be in buckets. Now that's not ideal, right? But for our purposes, we want to see it happen and make sure it works for us here. Make sure we can get those double values in here. Let's see if this one goes. So we'll step out a couple times, get that value cranked up a little bit here, like to over 10. Okay, so now we're at value 11. So we should see in here now, our storage is still size 10. Some of these now have more than one value here. Right? We have a key of 0, value of 0, and we have a key of 10, value of 10. We've got two different items in here all at once. So if we just run to the end here, well, let's take the breakpoint out and run to the end, we should see all the items come back out. We still get them all back out. Now, eventually it did resize here. But depending on what our load factor was here. So if we said, let's put this up to 3.5, right? When I run it here, I'm not going to get the values out in the same order. And this is why dictionaries can't guarantee order, right? Because this is I'm just grabbing them by bucket here. There's no sorting happening here. It just happened to be in order before because our storage was expanding and the numbers hashed really nicely here. So generally, you don't get that sort of thing here. You don't get the order in is the order out because there's no guarantee here. So we'll run it at like 75% and works great. Can yield all of our items. Okay, so they seem a little scary. Again, there's a lot of other advanced technical things we can do, but this is sort of the easy route to kind of understand how they work. Right? We make that oversized storage, and then we just start adding buckets here. Right? Not too bad. So what we could do if we really wanted to, we could make this a two-dimensional list to start. And that could work for us. That's not too bad. Now, what gets funny here, though, is if I were to make my own class here, make a class for, we'll just call it, how about coffee? We'll define in the knit method here of, we need a size, and, cream and sugar. So we'll assume cream here. We'll assume that one's none, and we'll assume sugar. How about creams and sugars? Creams is 0, and sugars is 0 as a default here. So you tell me what size, and then how many creams and how many sugars here. We'll take self.size as the size. Self.creams is the creams. And self.sugars is the sugars. Okay, so I can make some coffee. So if I wanted to, then I could have, a small coffee equals a coffee that was small. This is small black coffee, right? It's just coffee small, and then I could have a large coffee with cream and sugar. And sugar, or what do we call that? That's the double-double or something? A large double-double. So that's a large size with 2 cream and 2 sugar, right? Double cream, double sugar. Okay, and then if I take my crappy dictionary and I try and add something with a key of large black coffee and say, hey, maybe this one costs $1.99, and then, if we're like building out a menu here, take our crappy dictionary key of the large double-double and say, hey, that is $2.99 or something here. Right, let's give that a run. It runs okay, but let's see what happens to them when we hash them. Oops, sorry, I was supposed to do debug. So let's do one more here. So let's say we made a mistake here, $2.99 and $3.99, and see what happens with our dictionary. So let's run this in debug mode. So we're going to just step over here. So we have our crappy dictionary. It has its internal storage here. So we have one item here at 0, one item here at 7. I don't know which is which, but that's fine. So here is the key is the coffee. So the small, 0 cream, 0 sugar is here. And then the large here, right? The key value, large, associated value is $2.99. Looking good so far. So let's step into here and let's go check what happens. When we get our index out, we get index 7. Life is good. We have the value. The key matches the key. So we update the value. No problem here. We updated the value. But now if I make another large double-double again here, when I use this one and I say, hey, it should be the same thing, right? It has the same attributes. Here, let's see what we get. Run this in debug mode. So we're going to step over, and then we'll step into this one. So we can see in our crappy dictionary here, now our items are at 2 and 4. That's not where they were before. The hash that you get is dependent on the object hash, which is dependent on your memory address, which is super weird. So it's based on your memory address here. So when this large double-double again, it should be the same thing, but it's not the same thing. So it got an index 6. I said, oh, there's nothing in index 6 here. So now I have the same, essentially the same object, but they're not the same object because they're at different memory addresses. So as far as Python can tell, they're different objects because my class didn't implement an equals method here. We didn't tell the class how to figure out if it was equals or not. So we need to define an equals method. We're going to return self.size equal other.size and self.creams equals other.creams and self.sugars equal other.sugars, right? If we're all the same, we want to be equal here. If all of those match, then we should be equal. Okay? But just because we have an equals method doesn't mean they're going to hash to the same location. Uh-oh. We get an error. Unhashable type coffee. Before we didn't get that. So before we had the equals method, we could hash. Once you add an equals method here, have an equal method, you must add a hash to use in a dictionary. Right? It just doesn't work without it here because we can't hash it. So if we've added an equals method, then we need to define our own hash method here. And now this is dangerous. Danger zone, right? Hashing needs to be consistent, right? Must be consistent for an object. So if an object is mutable, meaning parts of the object can change, if I can change the number of creams and the number of sugars in my object, I can't use those in the hash. If I can change the object size, I can't use it in the hash. Because if I were to change it, when I go to hash it, it's going to look like it's in a different spot in the dictionary here. So you can only hash immutable object or immutable properties. Immutable properties. Immutable. Did I spell it wrong? I did. How do I spell immutable? Immutable. Okay. Immutable properties. That means is if the size can't change, then hash size. If it can change, then I have no way of doing this, and I have to use the object's version of hash, which is, hey, this is the same memory address. It is the same thing, but now technically it's different. Dictionary. Come on. Thank you. So we want to make sure that these don't change here. So I could return hash of self.size. Now the hash doesn't need to mean that they equal here. So different not equal objects can have the same hash. That's okay. Right? If we just want to say, hey, hash the size, but then we'll go look at equals to see, oh, do you have the same creams and sugars here? That's fine, right? Then all larges will hash to the same place. All smalls will hash to the same place. All mediums will hash to the same place. That's an option here. It's not great because that means if I have 50 things in my menu and the only thing I'm hashing is the size, I'm only going to have 3 buckets essentially. This is not getting uniform distribution. That means non-uniform distribution, which means worse performance in dictionaries. Right? We looked at these before. In a dictionary, it's constant time because you're hashing, you're looking in the bucket, and we assume there's not very much in the bucket because we're going to assume we have uniform distribution, and we assume we have this load factor happening here as well. So it should be fine, but if we do this wrong, it's not going to work. Or you could do this. You could just say, hey, return 0. Hash them all in the exact same spot. I don't care. That totally is fine. As long as it's defined, Python doesn't care. What that means now is I'm going to have a bunch of values all at index 0, right, in my dictionary. I'm only ever going to use index 0. This is real bad here. Don't do that, right? At least do something of, the self.size here. We could do that if we wanted. At least then they'll go to different places. At least a little bit. I'll have the smalls in a bucket, the mediums in a bucket, the larges in a bucket. So ideally, you have another thing in here, right, that we could hash. So not everything works well inside of a dictionary as a key here, right, depending on what it is. So, and then we'll say, for coffee in crappy dictionary, let's print the coffee and the crappy dictionary key of coffee. So we should add like a string representation here, right? So we can print it out nicely. Return self.size plus coffee with, oh, let's do this as a format, sorry. So we'll say a formatted string here. This is self.size, coffee with self.creams, cream, and self.sugars, sugars. Okay, just return the formatted string here. So I can print those out now for every coffee. And now the two match because our equals method says, oh, hey, if they're the same number, we'll make a match here. This is fine. Not a problem. We have our two coffees here. Okay, so we can build out our own hash map. We can use the hash map, but it's important when we're using objects as keys. Hashing is super important and difficult sometimes. It can be really hard to do that. So we just have to be careful. All right, so if we wanted, then we could have return, was it super dot hash of self? If we wanted the object version of hash here, then my two large coffee again will be different. Nope, did I do it wrong? Super dot hash. Do I just call hash? Yep, okay. So now these are different because we're using the memory address, right? That's for object version that uses memory address. Return hash of self.size. Again, size isn't great. Maybe we could use creams and sugars too, but if that can change, like, hey, here's my coffee, and then I want to add some creams and sugars, that property might be mutable. So if I can say add cream and add sugar to the same instance of coffee, I can't use it as a key in a dictionary. And maybe you don't want to use it as a key in a dictionary. That is a choice too. So you got lots of possible gotchas there. All right, so let me get this committed to GitHub. And I think we'll call that an afternoon. We'll come back for lab on Tuesday then. So what do we have? So we already have some trees here. So we'll look at turning them into search trees for lab time. Does that sound like a good plan? Or would you rather just, no, I'm sorry, we can do the lab on maps. We'll do a lab on maps. Okay, that's what we'll do on Tuesdays. And then we'll come work on search trees on the 5th, and then sorting and selection, okay? All right, so let's do that. So let's grab 2001 here. Here's hash maps, commit and push. Maybe it'll push. All right, folks, you take care. Let me know what I can do for you, and if not, I'll see you on Tuesday. We'll talk about hash maps in lab. We'll get into search trees in class, and we'll talk about the final project as well. We'll have all of April for that. All right, so they're not called hash maps, Dota, but it is a map using hashes. So we just call it a dictionary in Python because Python's funny like that. So Python it's a built-in like first-class type in Python. It's not even like the name of a class. They're just built-in dictionaries, which are super cool. All right, folks, take care. I will see you around.